Okay, so we're going to be doing E&M Test 1 problem number 2, and we're going to be talking about RC circuits. So basically a general overview of RC circuits. The whole point of the circuit here is to charge up this capacitor so that we can use it as a power source for some other use. So basically this voltage source here is charging up the capacitor, so current's going, as soon as the switch closes, current is traveling from the battery to the capacitor and charging this capacitor up. So at the first instant that the switch is closed at t equals 0, the current's going to go through the capacitor back to the battery and it will be a full circuit. However, as the capacitor is charging up and when it's fully charged, the current in the circuit is going to end up being 0 because once this is fully charged, charge cannot move from one plate to another anymore. Another quick thing to note is that positive charge will end up on this plate and negative charge will end up on this plate over here. That's just a side note just to understand the circuit a little better. So let's take a look at the problem. Your engineering firm has built the RC circuit shown above. The current is measured for the time after the switch is closed at t equals 0, and the best fit curve is represented by the equation 5.2 e to the negative t over 10, where I is in milliamperes and t is in seconds. So just looking at the current, we can see here that it's going to be some sort of a decay, and if we take a look at the graph, this makes total sense. So knowing capacitors, the first instant when the switch is closed, the current's going to go through the capacitor quickly and come back to the battery, which means that at the first instant at t equals 0, there's going to be some max current here. As the capacitor is charging, the current is starting to slow down, and when this is fully charged, current can no longer move in the circuit. So at the time when the capacitor is fully charged, the current will be 0 and it'll be in a decay form, and so this graph here matches the function that we have, so that makes sense. For part A, they're asking us to determine the value of the charging voltage V naught predicted by the equation. So we're going to start with V naught equals IR. Now, they're asking us to basically find the value of the voltage at t equals 0 as soon as the switch closes. So in order to find V naught, we need I and R. R is given to us as 50 kilo ohms, and I we can find from this equation at t equals 0. So we're going to evaluate the equation at t equals 0, and we know that this is equal to 1. So I is equal to 5.2, and the problem did specify that I is in milliamperes, so 5.2 times 10 to the power negative 3 amps. So V naught is equal to I 5.20 times 10 to the power minus 3 amps times the 50 kilo ohms. Remember, it's kilo ohms now. When we evaluate this, our final answer is 260 volts. So, as predicted by the equation, when the switch is closed at t equals 0, the voltage is 260 volts. For part B, they are asking us to determine the value of the capacitance as predicted by the function. So there are a couple ways of doing this. I usually stick to a sort of simpler way because the other way is using integration, and that can be a little messy. So basically what you need to recognize, so if we look at our equation once again, so if you can remember this general form, it usually helps for these kind of problems. So the important thing here is that we have negative t over tau. So we can find the correlation between these two, that tau in this case is equal to 10 and A is equal to 5.2. But our interest here is tau. So an important equation to remember is tau, and this is for RC circuits, is equal to RC. Tau is a time constant, so tau is equal to RC. In this case, we know that tau is equal to 10. We know our resistance was 50 kiloohms, so we can easily solve for C in this case. C is equal to tau divided by R. So tau is 10 seconds, and R was 50 kiloohms. So if we evaluate that, we have 2 times, we have 200 microfarads for our capacitance. Looking at part C, they're asking us the charging voltage is measured in the laboratory and found to be greater than the predicted value in part A. So in part A, we found the charging voltage to be 260 volts, and now they're asking us that when they measure it, it's actually greater. So why is it that it's that the laboratory results are greater than what's actually predicted? So there could be several reasons for that. One reason is that there's resistance in the wire in the circuit. So looking back at the circuit over here, if there's resistance in the wire, then the amount of current that's actually moving through the circuit is going to decrease because your net resistance will go up. If the net resistance goes up, then voltage must go down if the current is constant in the circuit. Another reason could be that there's internal resistance within the power supply or the battery over here, and the same situation's occurring where the resistance is up and the voltage is going down with a constant current. Part 2 is asking us to explain the implication predicted for the value in the capacitor. So basically that means that the capacitor value that we've calculated is too high to the actual value, and the actual value is actually lower. So if we take a look at this equation here, so Q equals CV is the relationship between charge, capacitance, and voltage. So if we see that the actual value is actually higher than so if V goes up, then C must go down. Then the value that we've calculated here is actually a bigger value than what is actually going on in the circuit with all the resistance, taking all that into account. So now moving on to part D, they're asking that your laboratory supervisor tells you that the charging time must be decreased. You may add resistors or capacitors to the original component and reconnect the RC circuit. In part 1 and 2, we will show how to reconnect the circuits, basically. So looking at part D, we have, so this is what's given to us in part D, D1. They gave us a battery, and they gave us a switch. We have a resistor, a capacitor. So this is basically what's given to us to start with. However, this is basically what we had in the beginning, but they want the charging time to decrease. So what are they're asking us, what can we do to the circuit so that the capacitor will get charged faster, so that there's less resistance to movement of the current. So quick thing to remember, so for part I, they're asking us we can add any resistors that are necessary in order to make the capacitor get charged faster. So a quick review for resistors: if you have resistors in series, then you're going to add the resistors together. If you have them in parallel, so that's a summation. If you have it in parallel, you're going to add 1 over. So looking at these relationships, it's clear that if you add it in parallel, your net resistance in the circuit will decrease. And if you have net resistance in the circuit, more of the voltage over here can actually get transferred to the capacitor faster. So what we're going to do is add a resistor in parallel. So now what we're doing is we're decreasing the resistance here so the current can actually increase and get to the capacitor faster. So if you look at V equals IR, resistance goes down, then voltage and current both go up. Okay, part D2, similar sort of situation. They've given us the battery. They've given us, I won't draw everything in yet. They've given us a switch here. They've given us a resistor. We have a capacitor. And they're asking us, this is the voltage, capacitor, resistance. Okay, they're asking us, instead, for this situation, we have to use a capacitor so that we can decrease the charging time. So review for capacitors now. If you have capacitors in series, then you will add them like so. If you have them in parallel, you will add them like this. So basically we can see that resistors and capacitors are sort of switched, so in this case it won't work for us to put the capacitor in parallel, because if we put it in parallel, net capacitance will go up, and if net capacitance goes up, then the charging time will also go up. So if we look at the capacitance in series, we know net capacitance will go down. If net capacitance goes down, charging time will increase. So we're going to add in a capacitor right here. So that's what we've added in here, and for part D1, this is what we've added in here. And that is pretty much it.